Okay, welcome, good people. We're going to see if we can do this lesson in about 10-15 minutes. We'll see. Okay, exponential functions. So it's a new parent function that you're going to want to commit to memory of what it looks like, and then you're going to be able to do all kinds of transformations with it. So I'm going to start with number 2 because that's what I want to start with. So this is f of x equal to 4 to the x, and notice the x is in the variable is in the exponent position. That's what makes this an exponential function. Exponential function, when the variable is in the exponent position. Now, you can make a little table of values to get you started to generate the shape of this curve, and I usually do something like this. That gets me started. So substituting it into your function, x, you're going to have 4 to the negative 2, which is the same thing if you remember your properties of exponents. 1 over 4 squared, which will be 1 over 16. And then we're going to do 4 to the negative 1, which is going to be 1 over 4 to the first, which is just 1 over 4. 4 to the 0 is 1. 4 to the first is 4. And then 4 to the second is 16. So now we can graph those. So I've got negative 1 and negative 2 and 1/16, which is going to be real tiny. Negative 1 and 1/4, which is still small. 0 goes through 1, 1, 4, and then 2, 16. So then your function looks like, when you fill it in, and you can keep on doing some to the left of negative 2, but I hope you'll realize that anything to the left of negative 2 is just going to get smaller and smaller y values. And it's going to approach a horizontal asymptote. So the horizontal asymptote in this case is y equals 0. And that's true for the parent function. So this is a pretty basic function in that it doesn't have any transformations. The 4 can change. It can be 2, it can be 4, it can be 5. It'll never be 1, and it'll never be negative. So you've got y equal to a to the 6th, where a will never be 1, and a is always positive. Now here's a funny thing, because sometimes you can have a negative in front, but the a value is still considered positive. And that negative in front is going to look like this if you really wanted to analyze it. So what does a negative 1 in front multiplied to a function do to it? What effect does it have? It has the effect of reflection in the x-axis. So it would be an upside down shape. So exponential functions, the basic function is going to look like this, where you have some number raised to a variable. That base, the a value is called a base, will never be 1, it'll always be positive. And I usually only graph the asymptote, the y-intercept, and then I'll just do one more point, like 1, comma a. So if you substitute 1 into the function, you would get the value of the base. So usually those are the 3 things that I would plot on my graph to be able to sketch a true exponential function. And then if you need to, then you can do any transformations that need to happen. Okay, so looking at this number 1 question, f of x equal to 1/4 raised to the x. How does that look different than the one that we just did? Well, it's very similar, actually. And if you remember your properties of exponents, which I'm going to rewrite 1/4 as 4 to the negative 1. So if I rewrite 1/4 as 4 to the negative 1, those two things are equivalent, then I can do a transformation. So if you do your properties of exponents, so if you have power raised to a power, they get multiplied. And this is what I could graph. I already know what 4 to the x looks like, but what does the negative on the x, what effect does it have? So 4 to the negative x, so negative in front of x does a reflection in the y-axis. So instead of it being an increasing function, this one's going to be a decreasing function. So all of those points that we just made on the function over here, we just have to flip them to the opposite side of the y-axis. So instead of having 2, 16, you're going to have negative 2, 16. Instead of having 1, 4, you're going to have negative 1, 4. Now if it's on the axis, it stays there. And then instead of having negative 1, 1/4, we're going to have positive 1, 1/4, and then positive 2, 1/16. And your function would look like this. Now, those are the basic shapes of the exponentials. If the base is bigger, then the exponential function increases faster. That's really the only difference that's happening. And then you can also apply all the other transformations that we've already done. Translate left, translate right, translate up, translate down, and then of course you've got the reflections in the x and the y-axes. So let's look at a couple of these guys. I've got f of x equal to 1/2 to the x. F of x equal to 1/2 to the x. I can rewrite that as 2 to the negative 1 to the x, which is the same thing as 2 to the negative x. And if I wanted to just graph 2 to the x, then I know it's going to have a horizontal asymptote at y equals 0. It's always going to have a y-intercept of 0, 1 if there's not a number in front of the base. And then I'll do one extra point, 1 comma whatever the a value is. And if you need to generate that from a little table of values, you're welcome to do that. So 0, 2 to the 0 is 1, 1, 2 to the 1 is 2. So I've got, this would be my parent function with the asymptote on the x-axis. Oop, 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 go back, go back. Nope, not the right one. Where are you? There you go. Man. So that would be y equals 2 to the x, but what I really want is this one, which is going to be a reflection in the y-axis. So I'm going to just flip those points. It would look like that. So we can look at number 5. F of x is equal to negative 2 times 1/2 to the x. So I've already graphed this thing. I know what it looks like. Now what effect does this negative 2 multiplied in front have? Well, it does two things. The 2 is going to do a stretch. So stretch, vertical stretch by a factor of 2. And then the negative is a reflection in the x-axis. So I'm going to take that black graph right here. We're going to stretch it by a factor of 2 and flip it upside down. So if you want to, you can make a little table of values, but here's what I know. The asymptote, horizontal asymptote, is going to be the same. And instead of having a y value of 1 here, I'm going to have a y value of -2. And instead of having a y value of 2 here, it's going to be doubled, which will be 4, but it'll be upside down. So it's going to be here. And then you can do your graph. So that -2 multiplied in front did a vertical stretch, and it reflected it in the x-axis. So now let's talk about this one. We don't actually have to graph the whole thing if you don't want to. We can definitely talk about all the things that are happening. So the parent function would be right here. So it's the shape of 1/2 to the x. 3 does a vertical stretch. Negative does a reflection in x-axis. The 2, the +2, does a translation left 2 units. And the -1 is a translation down 1 unit. So I know it's going to be, so if you want to do a little sketch here, I know it's going to be this shape where that point is 0, 1, that point is -1, 2. And then I would do a vertical stretch by a factor of 3, and I would flip it over the x-axis. So that's going to put me stretched by 3. That new point would be 0, 3. That new point would be -1, 6. So I'm going to flip those over upside down. But I haven't done my translations yet. So I need to move those points to the left 2 and down 1. So left 2, down 1. Left 2, down 1. And then also notice that my asymptote is also scooted down 1. So now my new function is going to do this. Kind of missed that ordered pair there. So that pink line curve is the stretched, reflected, and translated exponential graph. And yes, you've got your calculator with you. You can verify all that stuff. So now, just remember your transformations. So this one, that's my parent function, which looks like this. But what's going to happen to it? This one moves it right 1. This one moves it up 1. So I need to move those points right 1, up 1. So I've got right 1, up 1, right 1, up 1, and the asymptote also moves up 1. So my new shape looks like that. Now let's look at this one, because this one's a little bit different and it's definitely on your assignment, but I didn't want it to be tricky for you. F of x is equal to 2 raised to the 3 minus x plus 2. 2 raised to the 3 minus x plus 2. So notice that the 3 and the x are kind of switched from the way we're normally used to seeing it. So let's rewrite it. So I've got negative x plus 3. So because addition is commutative, you can switch the two positions. Just make sure you switch the signs that go with it. So the 3 is positive and the x is negative, so it has to go together. And then, because we've seen this before and it's tricky, I'm going to remind you, you've got to factor out your negative so that you can find the true transformation. So now that we've got it factored out, I can now know that I've got 3 transformations happening. This one does a reflection in the what axis? In the y-axis. This is going to take it right 3 units. And then this one is going to do up 2 units. So we can start with the parent function if you choose. The parent function is going to be 0, 1. 2 to the first is 2. If you want to go another one, 2 to the second is 4. 2 to the third is 9. All those extra points are not necessary. Just thought that I would share them with you if you want a more precise graph. So what I've got right now is y equals 2 to the x. So then we can do a reflection in the x-axis. So all those points get switched to the opposite side of the y-axis. And then we also need to move them right 3 and up 2. So I'm going to try to do those all in one step. So this one gets translated over here. Not translated, but reflected. And then I'm going to need to do right 3 up 2. So right 3 up 2. This point gets reflected over here, and it has to go right 3 up 2. This point has to get reflected over here, and it moves right 3 up 2. And then the last one, I'll make it orange, I guess, is this one that doesn't get reflected because it's on the axis, but I still need to move it right 3 up 2. Oh, I forgot. I didn't move the blue one correctly, did I? Right 3 up 2. And then my horizontal asymptote has to also move up 2 units. So my horizontal asymptote is now here. And we can fill in our curve. What color do we like? So it's going to do one of these. And all that previous work is unnecessary. I mean, you don't have to show that work. Now on your, assignment, it's going to have you click the right buttons to get the right shape, and then it'll have you describe and possibly translate the functions appropriately. Okay, so now you're going to get into, actually the assignment starts with some problems like this, e to the some power. So e, it's kind of like pi in that it's a symbol that represents a number. E, and if you push it on your calculator, let's see, do I have a calculator? E, the E button, where is the E button? There's 2 of them. There's one right there underneath the clear button. No, I'm sorry, it's underneath the, it's the division sign. And if you press enter, you get 2.718 approximately. There's another place, and it is on the left column on the ln button, second ln, and then you have to put in an exponent of 1 and you'll get 2.718. So there's two places on the calculator where you can do it, and I don't have like a cursor to show you where they are. But E has the value of 2.71828188285, and it's a non-repeating, non-terminating decimal, similar to pi, but we usually just use 2.718 as an approximation. 2.718. So e to the first power is approximately, it's not exactly, so we're going to use the approximate symbol, 2.718, but it does continue on. And then put this in your calculator. It means the same thing as 1 over e squared, but you can type it in just like it says. So second button, and then the ln button, and then raised to the -2, and it gets you 0.135. Now this one, e to the 0, anything to the 0 is the same thing. It doesn't matter what the base is. So e to the 0 is always going to be 1, just like 2 to the 0 is 1, or 5 to the 0 is 1. Anything to the 0 is 1. So put that in your calculator just like it is, e to the 3rd, and you get 20.055. Nope. 80. Nope. Try that again. 0855. So part of your assignment is to know where your E button on your calculator is. Now you might be asking, why do I need E? Well, it comes up in these exponential growth models when we're dealing with different financial formulas. So let's look at number 18. I've got a formula there for you. A equals P times 1 plus R divided by N raised to the NT. So let's analyze that, I guess. A is your amount, your final amount. P is the principal, or the amount invested. R is going to be an interest rate, but you don't want a percentage. So you may have to change it to a decimal. N is how often this account is compounded, meaning how often is interest calculated. So this is the number of compounding periods. And then T is time in years. So here's the situation. Rob invests $6,572 in a retirement account with a fixed annual interest rate of 3% compounded monthly. What will the account balance be after 14 years? So this is going to be the P value. Now this is an interest rate, but again, you do not want a percentage, so we're going to change that from a percentage to a decimal point. So move your decimal point 2 units to the left. And then this will be our T value. Rob invests $6,572 in the account with that interest rate compounded monthly. So the compounded monthly, that's going to give you your compounding periods. So there's 12 months in a year. That's how many compounding periods there are. So you can write your equation, 6572, 1 plus 0.03 over 14, and then your exponent is going to be 14, and you can put 12 there. Now sometimes you're going to be asked to calculate this for multiple years, so I like to just put an X there, and then I can calculate it for different years. So if you'll put this in your y equals screen, then you can use the table to evaluate for multiple input values. So let's see if I can transfer that to my calculator on the next screen. Oh, you know what? I just looked at, this is a 12, not a 14. Oh, stop. My compounding period is 12, not 14. My year is 14. Okay, compounding period is 12. Sorry about that. So I need to put 12 for n. So going to my calculator, I'm going to go to the y equals screen. And I was practicing with this calculator earlier because I don't use it very often. 6572, 1 plus 0.03 divided by 12, raised to the 12x. And then I can go to the table, and I wanted to calculate for 14 years. So 14 years is going to give me $9,997. That's funny. $9,997.09. And then you can look at other years. So 20 years, you would get $11,966. But for this one, after 14 years, and it's going to ask you to round to the nearest cent, so always do it to the 100th. And that's what you're going to answer. So I've got one more just so that we can compare and contrast. Joe invests $7,331 in a retirement account with a fixed annual interest rate of 9% compounded quarterly. What will the account balance be after 18 years? You guys could pause this and answer the question and see if you're right. So let's see. This is going to be the p value. This is going to help us find the r value. This is going to help us with our compounding periods, and this is going to be our time. So after 18 years, he's going to get $36,000. Wow. That's a large chunk just by putting your money in the bank. Okay, now one of the questions that's in the assignment, it's going to give you some information like this child received a gift on her 6th birthday. How much will it be worth on her 13th birthday? So make sure you subtract the number of years that the account is active. Don't just put in 13 for the final year. And I guess one more thing we should reiterate, what transformation does a negative in front of the variable do in an exponential function? So it's talking about this. The negative in front of the variable in an exponential function. What can't speak. What does that negative do? Reflection in y-axis. Okay, I'm going to call that done.